In this unit, we will be covering the basics of water resources and their importance to people and ecosystems. To get us started, let's reflect on the following question. Do water resources shape society and cultural values, or do society and cultural values shape water resources? At this point, pause the video for 10 minutes and write down what you think, and the reasons or experiences you have for it. No matter your response to the question posed, it is hard to deny the interdependence that we have on our water resources. There are, of course, natural components of this cycle, including weather and climate, the timing of availability of water resources, the land use and land cover, such as either pasture land with grassy fields or urban centers with lots of concrete, but there are also anthropogenic forces that shape us in our water resources, including cultural and spiritual values, or merely politics. All of these components act to shape one another. Take a few minutes to write down how you use water on a daily basis. Think about how your lifestyle might alter the natural environment too. Considering our dependence on fresh water, it is shocking how little of it actually exists. Globally, fresh water only makes up 2.5% of all water resources, with most of this being locked up in glaciers and ice caps. Surface water, such as lakes and rivers, makes up only 1.3% of freshwater sources. Later, we will learn that groundwater resources are often linked to surface water sources too, and are not just necessarily separate, as this image might lead you to believe. As we look at the water cycle, we know that the amount of water on the planet is not changing. Even with changes in climate, the amount of fresh water is not diminishing. Rather, the places where fresh water is being stored are changing. As an example, the melting of ice caps will free up fresh water, and these can be stored in the atmosphere, underground, or in the ocean. We use fresh water in countless ways, predominantly for agriculture, which you see on the left, but also for municipal supply and industrial supply. You can see on this graph that over time, our demand for water has grown and is projected to continue increasing with population growth and our quality of life. Now that we've gone over some of the natural and human forces affecting water resources, let's talk a little more about how to conceptualize these problems at a finer scale. In hydrology, we often refer to the natural boundaries of water flow as watersheds, or basins, and these mostly characterize how rivers flow and converge, but groundwater, again, is another important component of these basins that feeds into streams and rivers. Because of the importance of watersheds and the scarcity of water in the arid West, John Wesley Powell, who was the director of the United States Geological Survey for 13 years, envisioned that water be managed in the West with respect to watershed boundaries rather than just political ones. In the background of this slide is a picture of these watersheds, which was published in his report on the lands of the arid regions. Powell believed that managing water within watersheds would promote long-term conservation of a scarce resource. Walker Lake has been one such area that suffers from overuse. Water from the lake is primarily diverted for irrigation, and water levels have decreased in the lake by 140 feet in approximately 100 years. And at the same time, the concentration of salt, or salinity, and total dissolved solids, TDS, are on the rise, going above lethal levels for the native fish. Many research and conservation efforts are ongoing to revive Walker Lake. So if we were researchers on this project, what are some of the things we might consider? We would look at the river inflows and outflows over time and how those are being used for irrigation, municipal supply, or industry. We would think about how some of the water applied on irrigated fields would run off, going back into the river system, or how it would infiltrate into the soil and back into recharging the groundwater levels. And we might also look at how groundwater resources contribute to both irrigated agriculture through pumping and to the river system directly. And of course, we would want to quantify these things with measurements of river discharge, looking at monitoring wells, perhaps doing some pumping tests. And we might want to know what irrigation efficiency looks like, as well as the crop use or requirements. This is also referred to as evapotranspiration. Let's pause here and think about what that means. Crop requirements, or crop ET. Basically, this is referring to a water footprint, or how much water it takes to grow a crop. Crops can be food, fuel, or fiber. And so, have you ever thought about how much water it takes to feed you breakfast every day? The eggs, the banana, or the glass of milk? Or how about how much water it takes to make your cotton t-shirt or your leather shoes? To provide an example, to grow a single apple, it takes 125 liters or 33 gallons of water. For a glass of apple juice, it takes 230 liters, which is about 60 gallons of water. Now, we can break this up into even finer components by looking at different kinds of water. You, of course, know about blue water, and this is the kind of freshwater sources that you would naturally think of. But there's also the water in the soil at the root zone for the plants, and this is called green water, and the kind of water that is used for diluting pollution, which is called gray water. Looking around our kitchen, here is a visual of typical water footprints for each kind of food. And we can see that generally meats require more water per kilogram than things lower on the food chain, like starches and fruits and vegetables. We can also take a look at water footprints of our biofuels, seeing that soybean fuel is the most consumptive of water. Another factor to consider when thinking about a virtual water footprint is that we are a globalized society. We import and export goods, especially food, to and from all over the world. And in the map shown here, countries that are high net water importers are shown in red, while countries that are high net water exporters are shown in green. So, for example, the U.S. is a net exporter of water, mostly in the form of wheat, and India is mostly a net exporter also, but in the form of cotton. Dry countries, those that are heavily developed, such as Europe, and those with poor soils, are net importers based on the need to bring goods into the country for human consumption. Therefore, the total water footprint for a country is both the amount of water consumed and imported and the amount of water exported to other countries. The U.S. is both one of the largest consumers of water as well as being one of the largest exporters of water, which is why it has one of the worst national water footprints as compared with countries like China and India. Let's think of some of the implications of this. We talked about this at an international scale, but we can think of these at a more local scale too. And so let's look at these questions. Is virtual trade set up based on the need or based on past trade agreements? So yeah, at an international level, it's the latter. But what about at a regional level? Does it make sense to use water resources in one location? Perhaps exporting elsewhere? Think of some alternatives too. And then, is there a better way to trade virtual water to ensure human health, economic vitality, and environmental sustainability? So think of some ways to do this. Just take a few minutes to answer these and we'll come back. For the next few minutes, we're going to talk about water scarcity, which compares how much water a region uses compared to how much water is available. Usually, when we think of water readily available to a community, we focus on blue water. So scarcity is merely the proportion of the blue water footprint to the blue water available. This graph is of river flow over 1 year for the Colorado River. And this is called a hydrograph, which we will discuss more in detail at another time. But here we can see two curves, the natural runoff in black and blue water available in blue. Natural runoff is simply the river flow in the Colorado River if there were no alterations to the system and it was allowed to flow naturally. And because the Colorado River is snow-fed, its hydrograph peaks in the spring between May and June, and then it declines to much lower flows over the fall and winter months. Now, blue water availability is more specifically the amount of water that can be consumed by humans that will not impact river ecology. And so the assumption here is that the amount of water available is equal to 20% of the hydrograph, what's in black. So this means that a river can only give up 20% of its natural flow. On this slide, we also have the blue water footprint, or consumption. This is plotted in green. And it shows that during April and May, the consumption, or the blue water footprint, is less than what is available. But starting in June and throughout the summer and fall, the blue water footprint is larger than what is available. That kind of sounds like a problem, right? And so try to think about why this might be the case. What's driving this result? Okay, let's look at the blue water scarcity. The units are in percent, or 100 times of what the fraction is. And scarcity shows when more water is being consumed compared to when it is available. And perhaps we can define the following, and we can say that low scarcity is when the ratio is less than or equal to 1, or 100%. So in other words, humans are consuming less than the amount deemed available, or using 20% of the natural runoff. So when is this happening in the Colorado River, when we have low water scarcity? And what do you think is driving this result? We can also define significant scarcity at the ratio when it falls between 1 and 2, or 100 and 200%. So at 200%, humans are consuming twice the amount of water than is available. And to translate, if 20% of the natural runoff is available, then twice as much would be 40% of the natural runoff for any given month. And so when is this significant scarcity occurring, and why? And finally, we can think about severe scarcity as being anything larger than 200% or greater than twice the amount of water available. This means that anything larger than 40% of the natural river flow. And so when is this happening in the Colorado River? And explain why you think it occurs when it does, in the fall and in February. And look at what is available and what is being consumed. And what do you think is more indicative of the system stress, availability or consumption? Looking at the annual totals, the scarcity level is significant, right? Because it's between 100 and 200%. So if we look at the annual result, do you think that this characterizes the system behavior in trying to manage for a more environmentally or ecologically sustainable system? In other words, why do you think that looking at monthly behavior might be important for watershed management? Water scarcity is an issue worldwide, such as in the Indus River Basin, where so much groundwater depletion is occurring that it jeopardizes drinking water sources. In the Rio Grande, which crosses the international boundary between the United States and Mexico, water levels drop so much that pollution concentrations become especially high, killing native species of fish. The indicator is useful in some ways, such as helping us understand where conservation efforts are most needed, but in other ways the indicator has errors. For example, it doesn't factor in the consumptive water use by different sectors, and this then ignores return flows by things like agriculture and industry, and then probably overestimates water scarcity. In other ways, it ignores the transfers of water resources between different basins. And this happens commonly, for example, in federally funded projects in the western United States. So thinking of Colorado and California, Arizona, Nevada. And further, the indicator does not consider the difference between contaminated and uncontaminated water resources. And so in these last 2 points, the indicator may be grossly underestimating water scarcity.
On the INSTREAM website where you found this video, you will also find an Excel spreadsheet. The spreadsheet has two worksheets, one containing monthly data for the Republican River and the other worksheet containing data for the Mississippi River. Using the data provided in that spreadsheet, calculate water scarcity per month for the two river systems. Use that data to answer the first two questions. Compare the natural river flows in these two systems. How are they the same and how are they different? Use your data specifically to explain. Then compare blue water availability between the two systems. Again, use the data to explain the similarities and differences. For the final two questions, if your teacher has already assigned you a client group, then answer these two questions from the perspective of that client group. If you're using this as a standalone video, take on the perspective of a particular stakeholder group, such as farmers, fishermen, or parks and recreational users, or choose another stakeholder group that you're more familiar with, and then answer, what level of scarcity exists in these systems? When does river water become most scarce? Why is one system more stressed than the other? And what kinds of management alternatives would you hypothesize to help? Then, how do you think virtual water imports and exports impact these river basins? Can this be modified without impacting regional economies? You may need to consider short-term versus long-term economies and the issue of economic sustainability. If you're using this video as part of the broader unit, these two last questions will feed into the argument you make for the court.